Welcome to my video from the Big Bang to First Light. In this video I wanted to take a quick run through the history of the universe, highlighting some of the things that we think we know and some of the things that we don't know. Part of the reason I wanted to do this is because this is just cool, but the other reason I wanted to do this is to give people a flavor of some of the scientific motivation for the research I do. So let's start with the Big Bang. So the current best theory we have about how the universe began is that the universe began as a very small and extremely dense ball of energy. And this ball of energy, so small, and I'll just draw it as a little dot over here. But this ball of energy was so dense and energies were so high that quantum fluctuations dictated that every once in a while there'd be a little more energy in one part of this ball than in other parts of this ball, just by quantum fluctuations. And we're talking about really small differences, but these small perturbations are extremely important because they are what give rise to all the structure in the universe that we see today. So we don't have a lot of information about this epoch, but this is called the PreInflation Epoch. And we know that the universe spent enough time in this pre-inflation epoch that energy could flow back and forth across the size of the universe and bring this whole ball of energy to almost the same temperature, except for these quantum fluctuations. And then suddenly, for a reason that we don't really understand very well, the size of the universe began increasing exponentially with time. From this tiny little ball of energy, which people suggest may have been around the size of the head of a pin, to a truly cosmological scale. And this exponential growth in the size of the universe is called inflation. Now, how could this happen? How can space itself have expanded exponentially in inflation? Well, to understand why the universe might inflate, maybe we should first ask, well, what would cause the universe to contract? And the answer is gravity. Gravity holds the expansion of the universe in check. And this is slightly more complicated than the statement that gravity pulls things down. Gravity, as we understand from general relativity, actually warps space. So when we talk about gravity here, we're not talking about the perceived force of gravity, which pulls an apple down towards the ground. We're talking about the bending of space-time that curves space around and holds it to a finite size. Now we know the force of gravity, G, is proportional to mass. And we also know from E equals mc squared that mass and energy are essentially the same thing. So the expansion of the universe depends on how much energy is in the universe, or the energy density of the universe. And this energy density can come from all sorts of things. It can come from the energy of photons, of light going around in the universe. It can come from particles moving around in the universe like neutrinos, protons, electrons, and so on. And critically, it can possibly come from space itself. So the current best idea for inflation is if empty space had a negative energy density, then if the universe expanded a little bit, it would create more space, which would have more negative energy, which would rob away some of the gravity holding the size of the universe in check, which would cause the universe to expand a bit more, and so on. And this runaway effect would cause exponential expansion, which is inflation. Now at some point this exponential expansion petered out into a much slower expansion. And again, we're not really clear on why, but a current possible theory is that the energy density of empty space may actually be an unstable quantity, such that when the universe started, it was stably in one state, and then through inflation, the energy density of empty space transitioned to a new value. And while it was transitioning, we had negative energy density, which caused the universe to inflate. And after the energy density of empty space closed in on its new stable value, the exponential expansion of the universe stopped. In any case, we now observe today that the universe is quite large, and the little quantum fluctuations in the pre-inflation state got inflated to cosmological scales here. So the universe was not perfectly homogeneous. In some areas there's a little more energy, and in some areas there's a little less energy. And this is important because if the universe were perfectly homogeneous, every point in space would look like every other point in space, and there would have been no way to form clusters of galaxies and stars and all of the important things in the universe that we observe today. So these quantum fluctuations formed the seed perturbations of all structure in the universe. So then what happened? Well, if we rescale our plots again down, the universe was still much smaller than it is today, and has been undergoing a much tamer linear expansion known as Hubble Expansion. And as the universe expanded linearly, the temperature of the universe has been dropping. So the universe has been cooling down. So what happens as the universe cools down? Well, early on, energies were so high that photons coming in could spontaneously break into a particle and an antiparticle, which could then combine with other particles and antiparticles coming in from somewhere else and create photons again. So early in the universe, energy was constantly sloshing around between photons and particles and back into photons again. But as the universe cools down, these photons stopped having enough energy to create particle and antiparticle pairs. So at various stages, as the universe cools down, different particles freeze out. And because it takes more energy to create the more massive particles, these particles freeze out in order of decreasing weight, with very massive particles, such as, for example, Higgs particles, freezing out earlier, less massive particles like protons freezing out later, and then even after that, you'll have electrons freezing out. And finally, latest of all, you'd have particles like neutrinos freezing out, where we're not even sure whether neutrinos have mass. Now here, after inflation, we have another of the big mysteries in the beginning of our universe. The second big mystery is dark matter. Well, what is dark matter? The answer is we really don't have a clue. But we think it exists for a couple of reasons. One is that if you measure how galaxies are rotating, you can figure out how much mass is inside of a galaxy. And by measuring the rotation curves of galaxies, we find that there's a lot more mass in galaxies than we see in the form of stars or gas or light. And it's not just that we're falling short in tallying up the matter, but we can also tell that this dark matter is distributed much differently than the rest of the matter in galaxies. That it's distributed on a much broader scale and extends much further out than the rest of the matter that we see in galaxies. Another reason we think there might be dark matter is that with precision measurements of the cosmology of our universe, which I'll talk about a little bit later, we can measure the energy density of the universe and how it's been changing as the universe has expanded. And similarly, from those measurements, we find that there's extra mass in the universe. It exhibits the same kind of properties as regular matter does as the universe expands, but outweighs the rest of this ordinary matter by almost a factor of 4, which is to say, if you took all the matter, about 85% of the matter in the universe is dark matter, and only 15% of the matter in the universe is the so-called normal matter. So why am I bringing up dark matter here? Well, one of the leading theories for what dark matter might have been is some of the most massive particles that froze out as the universe began expanding. And because these dark matter particles would have been one of the first to freeze out, this dark matter would have stopped bouncing off of photons and all of the other particles, which acted as a pressure holding particles away from one another. And these dark matter particles would have started themselves falling towards each other under the influence of gravity. And these areas where dark matter started piling up came from the dense regions where quantum fluctuations in the early universe created a little extra energy, which meant that there were a few extra dark matter particles in those areas, which caused gravity to be a little stronger in those areas and to attract particles towards these overdense regions. So early on in the expansion of the universe, right after dark matter particles froze out, we would have what are called dark matter halos, which created these sort of gravitational wells into which the rest of the plasma in the universe, the rest of these particles and photons that are all interacting with each other, would fall. That all said, one of the hallmark predictions of dark matter being massive particles is that we should occasionally be able to detect them decaying. And to date, nobody has managed to convincingly detect a dark matter decay event. And some recent experiments are starting to suggest that such decay events might not exist at all, which would be a major blow to the theory that dark matter is massive particles. It's worth mentioning that there's a competing theory to explain dark matter called MOND, which essentially suggests that our theory of gravity is wrong on the largest scales. Now, this theory is still under development and has some attractive features, but still struggles to naturally incorporate something akin to dark matter halos, whose gravity helps form structure in the universe. So let's continue our story down here. As the universe continues to expand, it gets cooler and cooler. It has these dark matter halos where there starts to be a little extra gravity, and more particles are freezing out, until at some point we start having protons freeze out of this photon bath, and also a lot of electrons. Now, a third big mystery in the history of the universe is why, when all these particles froze out, were there not an equal number of matter and antimatter particles? So as we said, all these photons should have been splitting into these particle-antiparticle pairs, which would all annihilate into photons. So another big mystery is the matter-antimatter asymmetry. For some reason, which we don't really understand yet in particle physics, there must have been some mechanism which preferred producing matter particles, things like protons and electrons, with a slight excess relative to antiparticles like positrons. But for whatever reason, what we were left with in the universe were a bunch of protons and electrons and not their matching antiparticles. And this is fortunate. If there had been perfect symmetry between matter and antimatter, all of the matter in the universe would have annihilated out back into photons, and we wouldn't have had any particles out of which to build stars and galaxies. So what we're left with at this point in the universe are some pretty energetic photons floating around, along with some protons and some electrons. These protons and electrons attract each other, and if you put them together, they would combine into neutral hydrogen, which we'll denote with an H here. But these photons are still pretty energetic, and every time protons and electrons combined into hydrogen, one of these photons would come along and hit that hydrogen atom and split it back apart, ionize it into the protons and electrons again. So up until a certain point, the universe remained highly ionized, with protons and electrons floating around with energetic photons. These photons would bounce strongly off the protons and electrons, and also would strike hydrogen atoms and split them back apart into these free protons and electrons. But again, as the universe expanded from here to a larger size, these photons keep losing energy. And the reason for this is that photons have a wavelength which is embedded in space. So as space itself expands, these photons go to longer wavelengths. And longer wavelengths means lower energies, because energy for a photon is equal to the Planck constant h times nu, where nu is the speed of light over the wavelength. So longer wavelengths make for less energetic photons. Eventually, these photons stop being energetic enough to ionize hydrogen more rapidly than protons and electrons capture each other to form neutral hydrogen. So before this happened, photons, protons, and electrons were all held tightly in equilibrium with each other, with photons constantly smashing into protons and electrons and exchanging energy with them. But after the energy of these photons dips below this critical energy required to ionize hydrogen, then suddenly photons travel unimpeded in the universe because they no longer had the charged particles that they interacted so strongly with, these protons and these electrons. And similarly, these protons and electrons, which now are neutral hydrogen atoms, no longer had the photons pushing them around as a pressure that prevented them from falling towards each other under gravity. So now, all these hydrogen atoms that are left behind start collapsing down into these dark matter halos, these areas of extra gravity that were set up by the dark matter collapsing towards regions of overdensity in the early universe. And these photons, which now stream relatively unimpeded through the universe, is what we call today the cosmic microwave background, or CMB. And a lot of our best tests of all of the theories for what happened early in the universe, inflation, dark matter halos, the energy density of the universe, the order in which particles freeze out of the universe, is all related to precision measurements we've made with the cosmic microwave background. And it's called a microwave background because these photons, which once upon a time were energetic enough to split apart hydrogen into protons and electrons, which means that they were in the ultraviolet range of the frequency spectrum. As the universe expanded and expanded, eventually today we see that these photons show up with a characteristic temperature of 2.7 Kelvin with a characteristic wavelength of about 1 millimeter. Now, since the photons that were the background of the universe and were very involved in everything that happened earlier in the universe have now essentially decoupled from the rest of the universe, I'm going to stop drawing the yellow photons in these pictures, and I'm just going to start focusing on the neutral hydrogen and the dark matter. So after this epoch, which is called the epoch of recombination, we now have a universe with these dark matter halos and a bunch of wispy hydrogen gas, which I'll color green here, it starts falling towards these dark matter halos. And in 2 dimensions, it's easy to draw these inhomogeneities as these kind of compact regions. But in fact, in 3 dimensions, what these end up coming out at are these filaments. The dark matter halos are connected by filaments of higher densities with a lot of lower density gas in between. So we end up with these dark matter halos, which give rise to a filamentary structure in clouds of hydrogen. And these regions will eventually turn into what we see today as superclusters. And other little clusters of galaxies will be arrayed along these filaments, and each of these clusters will be filled up with galaxies, such as the Milky Way and Andromeda in our own local cluster, which isn't particularly large. And these galaxies in turn will be made out of stars that form out of these clouds of hydrogen. But at this point, right now, there aren't any stars. We just have neutral hydrogen collapsing into these filaments. And this is a period known as the Dark Ages of the universe. And it's called the Dark Ages because there were basically no sources of light other than this cosmic microwave background. So what's going on during the Dark Ages? Well, to start with, we have a bunch of neutral hydrogen sitting inside a broad dark matter halo here. So all of this neutral hydrogen is going to be trying to fall down towards the gravitational center of this dark matter halo. Inside of that dark matter halo, there are going to be fluctuations in the density of hydrogen, and there are going to be little clumps of hydrogen, which are again falling down towards making galaxies. And on the scale of galaxies, there are going to be hydrogen clouds, where hydrogen are falling into slightly overdense regions to try to form stars. So we have gravitational collapse on the scale of halos, galaxies, and stars. And it wasn't clear a priori which of these scales would kind of form first. Would you first get these halos? Would you first get the galaxies within the halos collapsing out? Or would you first get the stars within the galaxies forming? And we currently think that there was, based on simulations, inside-out structure formation, which is to say that first the stars collapsed out, then the galaxies formed, finally halos formed. Although I should mention that this inside-out structure formation is still a bit of an open question. So then on the scale of an individual star, we end up with this cloud of neutral hydrogen here, which is a bit denser towards the center as it tries to form into a star. But as hydrogen fell down towards the gravitational center of this star, it gained energy, just as anything gains energy as it falls. Which means that these clouds end up rather hot, until at some point the heat of this cloud creates a thermal pressure which balances out the gravitational collapse. And in the early universe, when all you had was essentially hydrogen out there, it was very hard to get the heat out of these clouds so that they could further collapse. Basically, the only way it was done was via molecular hydrogen, H2, which is a hydrogen-hydrogen molecule, which had quadrupole radiation, which is relatively weak, to cool these clouds. But because this was so weak, we end up with the fact that really the only way to form these first stars in the universe and overcome this weak cooling was we needed very massive clouds, such that the gravity could overcome the thermal pressure resisting the collapse. So the first stars that formed were these very massive O stars on the blue end of the spectrum. They were about 100 times the mass of our sun, and they only lived for around 1 million years. And when they die, these massive first stars undergo a supernova, where the hydrogen in them gets converted into a lot of other elements, like carbon, oxygen, calcium, iron, and in fact, all the elements heavier than hydrogen, helium, and a little bit of lithium were made in the cores of these stars and then got splattered out into the surrounding hydrogen gas by these supernovae. And this is something worth noting, that all the elements that you observe around you and that you yourself are built out of, all these elements were synthesized in the cores of stars, so were essentially made out of stardust. And one key consequence of having these higher order elements is that they then allowed these hydrogen clouds to cool more efficiently, which allows a new generation of stars, which have some of these heavier elements in them, to form new stars which were less massive. like our sun. So the last major epoch in the history of our universe is as we come out of the Dark Ages, where we had these dark matter halos, which gave rise to these filaments of gas, out of which these first stars form. We have a lot of other gas out here, sprinkled around here, which was also neutral, in between all the galaxies that were forming. And so the last critical epoch in the evolution of the universe is when the starlight out of these first galaxies comes out and starts ionizing the rest of the hydrogen that's in the universe. So this starlight, which came from our cosmic dawn, the first stars in the universe, ionizes the rest of the universe. And this process is called the epoch of reionization. So the epoch of reionization is essentially the destruction of the rest of the neutral hydrogen in the universe that lies between galaxies. So what we observe now is that on the largest scales in our universe, and let us not forget that the universe is still continuing to expand, almost all the hydrogen in the universe is caught up in galaxies, which are configured in clusters that are along filaments and are connected with each other. So all these dots here are clusters of galaxies. And in between these galaxies, there's no neutral hydrogen. They're just ionized protons and electrons. And within these galaxies, with our own Milky Way as an example, we have clouds of neutral hydrogen arranged in these spiral waves going around our galaxy, with stars of various sizes and temperatures forming out of these gas clouds, some massive stars being blue, less massive stars being orange, older stars, as they move from burning hydrogen to helium, become red giants, and we still have the occasional supernovae, which scatter gas and heavier elements out into the surrounding areas of the galaxy, which seed new clouds with heavier elements in them. And out of these clouds form stars like our sun, with these disks around them of heavier elements, out of which form little planetesimals which collide and clear out the surrounding material until we end up with little planets, such as the one that we happen to live on. And as we're learning today, nearly all stars in our galaxy have planets around them. And a rather large fraction of these stars with planets have planets that are approximately the size of Earth in regions where the conditions are approximately right to give rise to life. So we're finding today that something like 20% of sun-like stars have planets that are somewhat like Earth. And our galaxy has something like 10 billion stars in it. And our galaxy is just one of several in our cluster, which is not particularly large. And our cluster is just one little piece of a large filamentary structure in our universe. And on this planet that gave rise to life, and eventually intelligent life, we are building telescopes with which we're able to look back through cosmic history to observe many of these epochs in the history of our universe. And this is because light travels at a finite speed. So if this is where we live in our universe, regions that are relatively nearby to us, the light can get to us in a shorter amount of time than regions farther out. So if we look at nearby stars, some of the closest stars will take only 3 years for their light to get to us. But if we look at a nearby galaxy, their light will have had to have traveled perhaps more than 1 million years to get to us. As we look further and further out, there are regions of space that are 13 billion light years away. And our universe itself is only 13.7 billion years old. So there are regions right now that are 13 billion light years away, which means that we can see back to a time only a few hundred million years after the Big Bang. And the light from the early history of the universe in these places is only now traveling that huge distance to get to us now. So incredibly, we can now use telescopes to observe not just the stars and galaxies in our immediate neighborhood, but we're able to look back to try to find the signs of the formation of the first stars in the epoch of reionization. We're able to start investigating the Dark Ages to try to find the very first very massive stars that formed out of the gravitational collapse of the hydrogen into these dark matter halos. And we've managed to see all the way back to this cosmic microwave background epoch and observed light that the last time it interacted with matter was when it hit a proton or an electron before neutral hydrogen even formed in the universe. And this leaves us with the last biggest mystery in our universe, which is that we've recently discovered, by measuring the distance to faraway supernovae, that the expansion of the universe is accelerating, which means that this linear Hubble expansion that we've been experiencing is starting to give way to something else. And nobody is quite sure what that something else is that's causing the universe to accelerate in its expansion. But we think that the universe did this at least once already during inflation. So are we beginning to undergo another inflationary epoch? Or are we perhaps seeing the rise of a new form of energy that has a negative energy density that causes space to expand increasingly rapidly? Einstein predicted, and then later retracted, one such form of energy density, which was called the cosmological constant, and could straightforwardly be incorporated into the equations for general relativity. But is what we're seeing the cosmological constant or something more esoteric? That's something we have yet to figure out. And people have named this mystery the mystery of dark energy. Unfortunately, we're not really able to see any farther back than that, because at this point, the Recombination Epoch, light interacts so strongly with the rest of the matter in the universe that the history of anything that happened earlier has been erased from that light. So we can only indirectly infer what happened before the Recombination Epoch, during these periods of the formation of dark matter halos, the freezing out of various particles, inflation, and the pre-inflation epochs, are only accessible indirectly by how they would impact observables such as imprints on the cosmic microwave background, or in the geometry of the structure formation in the dark ages, and how it influenced the later formation of structure, galaxies, stars, and planets later in the universe. So that's the history of the universe from the Big Bang through the first light of stars to the first light of telescopes able to observe those stars.